Welcome to the Mechanics of Solids lecture series. In this series of videos, we're working examples with pressure vessels. A pressure vessel is a thin-walled object that carries an internal pressure by developing strains along the walls of the object, which are referred to as membrane stresses. Our learning objectives are to evaluate membrane stresses and strains in spherical and cylindrical thin-walled pressure vessels. Here's a first example. A cylindrical tank contains a volatile fuel under pressure. A strain gauge records the longitudinal strain in the walls. Tau ultimate is 98 megapascals, and we want a factor of safety of 2.8, because if the shear stress tau reaches greater than 98, it's in danger of failing. We're also given the material properties. We're asked to evaluate the longitudinal strain, allowable longitudinal strain, and associated radial hoop strain. The longitudinal strain is what's recorded by the strain gauge. Okay, so I'll summarize. Find epsilon longitudinal and epsilon hoop. And if we make a little picture of our pressure vessel and a stress block along the walls, the longitudinal direction will be our longitudinal stress and longitudinal strain. Okay. The radial direction will be our hoop stress and associated hoop strain, epsilon hoop. Okay, so first let's figure out what the allowable shear stress is in the wall. If the factor of safety is 2.8, then the allowable shear stress is equal to the ultimate shear stress divided by the factor of safety, 98 over 2.8, or 35 megapascals. Okay, so next we want to relate this allowable shear stress to the normal strains that are recorded in the walls of the tank. And while we could do this by first principles, we have a nice summary of equations that we developed in the class that we can refer to. And here's the list. First off, we should observe that we're working with a cylindrical vessel. So we'll use this set of equations over here on the right. With regard to shear stress, we have maximum shear stress in plane, PR over 4T, and out of plane is PR over 2T. So this one is going to control. So we'll say tau max equals PR over 2T. Now let's relate that to the strains. Normal strains in the plane of the walls, epsilon longitudinal, we'll start with that one, and that's the one that's recorded with strain gauge. Epsilon longitudinal equals PR over ET times 1/2 minus nu. Okay, I want to relate this to tau max so that I can simplify my calculations. And I can do that by simply rewriting this equation a little bit. I'll multiply top and bottom by 2. So I have a 2 on top, 2 on the bottom. I'll bring the e over here. 1/2 minus nu. Okay, let's rewrite this just a little bit. PR over 2T is tau max, or tau allowable is what we'll use, times, carrying this 2 through, we have a 1 minus 2 nu divided by E. Okay, so now we can evaluate epsilon longitudinal equals tau max, or tau allowable, 35 megapascals times 1 minus 2 times Poisson ratio of 0.3 divided by E, 210 gigapascals. We'll multiply that by 1,000 to convert it to megapascals. And this computes to 6.67 times 10 to the minus 5. It's unitless because it's a strain and our stress canceled out. We could rewrite this as 66.7 microstrain if we prefer. So that's the answer for epsilon longitudinal. Okay, for epsilon hoop strain, the equation that we need is this one right here. Again, let's remember that tau allowable equals 35 megapascals equals PR over 2T. Epsilon hoop equals PR over ET times 1 minus nu over 2. Let's write that in terms of tau allowable equals PR over 2T times the 2, multiplying top and bottom by 2, bringing the E over here, 1 minus nu over 2. Now I'm going to multiply this through. This is, tau allowable times a 2 minus nu over E. Okay, so plugging in numbers, 35 megapascals, and we have a 2 minus 0.3 divided by E, 210,000 megapascals, and that computes to 2.83 times 10 to the minus 4, or if you like, 283 microstrain, and that's the answer for epsilon hoop. Okay. Does the answer make sense? Well, so we found that epsilon longitudinal was equal to 66.7 microstrain. We know that the hoop stress is twice the longitudinal stress. Here the relationship between hoop strain and longitudinal strain is a little bit different because of the material properties, Poisson's effect. Nevertheless, the answers are both small. Hoop strain is larger than the longitudinal strain. So the answers seem to make sense. And that concludes this example.